Hi everyone, in this video we're looking at hypothesis tests for claims that involve two proportions. So here's our scenario. An advisor suspects that students who never visited the tutoring center are less likely to pass their math class than those who visit at least once. So they find a random sample, they see that of 75 non-visitors, 48 passed their class, and of 80 visitors, 61 passed. So we're going to use a significance level of 0.05 to test their claim. So step one is to state the hypotheses. The claim that we're making here is basically that when we compare the pass rates of the two groups, those who don't visit tutoring and those who do visit tutoring, the pass rate is going to be lower for those who don't visit tutoring. I'm calling that P sub n here. So our claim would be that P sub n is less than P sub t. Now you could also write this as P sub t greater than P sub n if you reversed it. You just want to be consistent about which group is kind of the first group and which is the second group, because that'll matter when we're putting in our sample information. The null hypothesis here is always going to be that the two proportions are the same. So the pass rates are the same for those who visit tutoring versus those who don't visit tutoring. But our alternative hypothesis is that the P sub n, or the non-visitors group, that pass rate is lower. Because of that alternative hypothesis, this is going to be a left-tailed test. I know that because of the direction of my inequality. Again, if we switched the groups, this would be a right-tailed test, but then you'd also switch the order of the sample values as well. Step two is to select the test statistic and the distribution. So for a claim about or comparing two proportions, the test statistic looks like this. So this is a z value. This is going to be in the normal distribution. And on top we have p1 hat minus p2 hat. Those would be the pass rates from each of the samples. We could also write this as pn hat and pt hat, but basically the first group and the second group. So the difference between those sample proportions. And then in the denominator, we have a square root, and we have a p hat here. This p hat is the same as sample proportion that we've seen before, but in this context, the p hat is what we call the pooled proportion. This is sort of like if we put the two groups together, what would the pass rate be? So p hat in this case is x1 plus x2. That's the number of people who passed in each of the two samples added together, divided by n1 plus n2. So the total sample of sample size for each group added together. So that's our p hat. In the formula inside that square root, we have p hat times 1 minus p hat. And then times, here we have 1 over n1 plus 1 over n2. So this is kind of similar to the test statistic we had for a single proportion, but because we have two different samples, we have kind of a combination of the two sample values. Step three is to choose a significance level alpha. In this case, the significance level is just given in the problem. This is our standard 0.05 value. Step four, collect sample data and then calculate the p-value. So we have two different samples. Group one is our non-visitors group, and group two is the people who did visit tutoring. Group one has a sample size of 75. That would be N1. Group two has a sample size of 80. And P1 hat is 48 out of 75. P2 hat is 61 out of 80. And we could also write these as X1 being 48 and X2 being 61. Those successes in this case are the people who passed the class in each of those groups. So if I was doing this with Excel or using a Z distribution table, I would plug these numbers into the test statistic formula we saw before, calculate that out, and then because this is a left-tailed test, I'd find the area to the left of that z-score. But I'm going to use Desmos to do this calculation. So here I'm at desmos.com. I'm going to open the graphing calculator, or you can go to desmos.com/calculator. I'm going to the plus symbol in the top left that says add item, and I'm selecting the inference category. Now we're looking at categorical data here, so I'm looking at the inference for categorical data section, and we want this first option, z-test for proportions. This is the same thing that we used for a claim about a single proportion, the only difference being that we're going to include two different samples here. So my sample one, this is the non-tutoring, non-visitors. The total number of students was 75, and the number who were successes, or those who passed their math class, was 48. And then I'm going to open up sample 2. The second sample, which is those who did visit tutoring at least once, had 80 students total, and the number who passed was 61. I click Create Test. This is creating a Z-prop test. If I open up the hypothesis test section, the null hypothesis is P1 minus P2 equals 0. This is actually the same thing as P1 equals P2, or the way we stated it previously, Pn equals Pt. Same thing, we're saying that the null hypothesis is that the two proportions are the same. So this is the null hypothesis I want, and then I'm doing a left-tailed test in this case. So in the image, I have the test statistic at the bottom, z equals negative 1.668, and the p-value at the top of the rectangle, 0.048. So that is the area to the left of this test statistic. This also represents the probability of seeing this sample result or more extreme, sort of to the left, if the null hypothesis was true. So we're looking at this p-value and saying, is this small enough? Is this result unlikely enough that we can say that, we don't think the null hypothesis is true? So moving to step 5, we have to make a decision and then state the conclusion. Again, we're asking, is the p-value small, or is the p-value small enough? That small is based on our significance level, which was 0.05. So because our p-value is 0.048, we're actually just under 0.05 here. So this would be a significant result, or we would reject the null hypothesis here. So rejecting the null hypothesis, we're saying that the evidence supports our alternative. So we would state the conclusion something like, there is significant evidence to support the claim that students who do not visit tutoring are less likely to pass than those that visit at least once. So there does seem to be evidence for this claim that tutoring increases the likelihood to pass a class. We're kind of borderline here, so this isn't super strong evidence, but it is statistically significant at that 0.05 level. If the results had been more extreme, for example, if more of the tutoring groups had passed, maybe 65 out of 80, we can see that that p-value goes smaller. That's it for this video. Thanks for watching.